Okay, in this video, we're going to look at simulation methods. Okay, so remember in some of the methods we looked at, like the multinomial probit, for example, there were a lot of integrals that needed to be solved, and usually we have to solve these things by simulation methods. Okay, so first I'll just start off with describing one of the first simulation methods considered. This one actually doesn't work so well, but I think it'll give us some intuition for how it works, and then we'll go on to describe some other methods. Okay, so this is a random utility model where there's only taste heterogeneity and no preference heterogeneity. So what does that mean? It means that, here, let me get the pen. Okay, only taste heterogeneity means just this. Preference heterogeneity would be the betas being random. So we're not having random betas, only the random error shocks. Okay, and they're assumed to be normal. So this would be like a multinomial probit model with j choices. Pij is the probability that person I chooses j. And then y is an indicator, which is 1 if I chooses j. Okay, and so we can write the likelihood this way. Okay. Oh no, I keep losing the pen, but okay, this is the likelihood. All right, and so P is the thing that we want to simulate. Okay, how to simulate this probability, because it could be, you know, multiple integrals. So here's one simulation algorithm. So for a given set of parameters, beta and omega, so omega is the variance of the errors. And so if they're j choices, it's j by j, the omega. So for a given set of parameter values, generate Monte Carlo draws. So what we basically do is we fix the parameter values and then we draw. Right, so given a beta, and then we draw a set of residuals, and we draw that R times. So R could be 100 or 500 or 1,000, okay? And then we simulate utility values. You know, so for each given parameter, you can simulate utility values, and then we simply count up the number of times that that the person made the choice K. So how many times was the choice K optimal within that simulation, right? So you drew the errors, say 100 times, and you observe the person choosing K 20 times. Okay, so then the probability would be 20. And you can put in x's. Did I have x's here? Let's see. Oh, z's. Right, so the person's characteristics could be in the model. You know, you just simulate utility for that person. All right, and that's going to be your estimator of the probability for that person that they chose that choice. Okay, and so then you just maximize the likelihood inserting that. So that's the simulation step, is just to get the P. Okay, so if you look at that Mansky and McFadden book, there's a chapter, I think, that studies the simulation methods, and it discusses how this procedure doesn't perform very well. And in particular, it runs into problems if P is low, you know, so if certain choices are rare. And then you see, like, especially if it was very rare because you're taking the log, you know, so if you did a simulation and nobody's making that choice, then you'd be in the position of having to take the log of 0, right? Okay, and then this is the variance of it's called the crude frequency simulator. Okay, so McFadden has a famous paper, which is very well cited. I mean, McFadden won the Nobel Prize. So this is, some of his important work. He provided insights how to improve the simulation method. And he showed that this method works well if an unbiased simulator is used. So I think that is unbiased. But that the functions to be simulated appear linearly in the conditions defining the estimator. Okay, this is not satisfied because the functions to be simulated here, you have log p. You don't have p in the conditions defining the estimator. Okay, and then the other thing is that the same set of random draws is used to simulate the model at different parameter values. So I'll describe what this means exactly. Okay, but condition B is violated for the crude frequency simulator. Okay, so let's look at like a different way of simulating the model. So this is now a slightly different model, actually. So in this model, beta is random, but epsilon is not random. Epsilon is random, but there's only preference heterogeneity, no taste heterogeneity. So there's only the beta, the most general model would have both. So it's only just for simple notation. It'll be straightforward how to extend it to allow for both. But this is just random beta. I just put the two cases so that you could see like either way how it works. Okay, and so the epsilon is just heterogeneity in beta. Okay, so Pij, so I'm going to put all the parameters in gamma. So gamma is actually beta bar and sigma epsilon. Okay, and the dimensionality of the sigma epsilon depends on how many characteristics there are. So the likelihood is this, which is similar to what we had before. And what McFadden did is instead of setting it up as a likelihood problem, he took the derivative and set it up as a method of moments problem. So here, take the derivative of this likelihood, Yij, and then you get, this is the derivative of log p here. Okay, now the sum of the probabilities equals 1. If you take the derivative and then you multiply top and bottom by this Pij, you can see that this sums to 0. So we can simply add this term to this previous term. Okay, this term here, we're just going to add this term to it. And so you can express the first order condition of the likelihood problem in this way. Okay, so why is that interesting? Well, this is like a moment condition, actually, because the expected value of Yij is Pij. Okay, so this is the mean of this. Okay, and this is like an instrument. Okay, this is like an instrument. I think it's actually on the next slide. Okay. Yeah, so the expected value of Yij is Pij, and then letting W equal this ratio, you can write this in a way that looks like moment condition from an IV problem. Okay, now we still have P in there, and now not only P, we also have the derivative of P, so we still have to simulate that. Okay, I guess the crucial thing that makes it perform better is that now P appears linearly. Like we don't have log of P, how we had before. Okay. So let's look at a simulation algorithm for this model. Okay. So what you can do is this epsilon here, you can apply Cholesky decomposition to the variance. So for any variance matrix, you can do a Cholesky decomposition on it. Okay, and you can write epsilon as this gamma matrix times EI tilde, where EI tilde is just normal 0I. Okay. All right, so the simulation algorithm, first we're going to draw these E's, and that's just from a normal 0 I, so they're IID across people. And how many draws? Well, we have n people, k characteristics, so the beta is length k, and the epsilon is taste heterogeneity, so the variance covariance matrix sigma epsilon is k by k. And then R is the Monte Carlo draws. Okay, so that's how many draws we need. Then we'll fix this matrix, because as you're doing the simulation, you're searching over the parameters. You start with a guess. You do the Cholesky decomposition on your guess. You compute these this is the taste heterogeneity, right? So you compute this. And you started with a guess of beta bar. And so then you would generate these utilities. So under those parameters, these are the utilities, and you do this R times for the different Monte Carlo draws. Okay, and then you can count up, like the frequency estimator is just you count up the number of times your simulation leads person I to make choice J. And you do that for each of the choices, so maybe like 10% time they choose this choice, 80% time they choose some other choice. Okay, and that's like under those parameter values, that's your simulation estimator for the probability that person I chooses J. And the crucial thing is that when you switch, to new parameter values, you compute the objective function, and then your optimizer is going to send you to some new parameter values. Well, when you get the new parameter values, you keep these epsilons the same. Like you don't keep redrawing the epsilons. Okay, so that was here when McFadden said, what's important for the performance of the estimator? That's this, that the same set of random draws is used to simulate the model at different parameter values. So you don't keep changing the E's, okay? The only thing is you change, the Cholesky decomposition is going to keep changing as you search over the parameter values, but you keep the E the same, because that's just, normal IID. Okay, so that gives you a simulator for PIJ. We also need a simulator for the derivative of PIJ. And for that, you can do numerical derivative. So if you have a simulator for your PIJ, you can always, compute a numerical derivative and simulate the derivative. So this is the numerical derivative. Okay, now you can do one other thing to improve the performance of this estimator. Okay, because one of the complications is this indicator function is not differentiable. Okay, and that actually, I think it's here. So it's not smooth due to the presence of the indicator function, and this causes difficulties in deriving the asymptotic distribution. And there are methods, like Pecos and Pollard have a famous paper about, how to get asymptotic distribution for non-differentiable functions. And I mean, quantile estimators, you have to deal with these sorts of issues all the time. But in this case, well, I mean, this is also true that Pij still cannot equal 0 because we're dividing by it here. So that you might still run into problems with with very rare choices, right here. Because you can't divide by 0. So you might need a large number of draws, to estimate so that you have some chance of actually drawing it for rare choices. Let's see. Okay, so but the problem of non-differentiability you can partly solve. Okay, there's a nice paper by Steve Stern called Smooth Simulated Method Moments, published in Econometrica, and it replaces the indicator function. So the indicator function looks like this. It goes from 0 to 1. Well, you can replace that with a smooth function, which kind of looks like a CDF. In fact, usually the function that they use is like a CDF, usually like a logit CDF. Okay, and the smooth function goes from 0 to 1 in a smooth way instead of in this choppy way. Okay, and that actually can improve the performance of the simulator as well. So this is called smooth simulated method of moments. Okay, how does simulation affect the asymptotic distribution? Okay, and that's really, I mean, these slides just don't have a lot of information on it. I just give you the result here. But if you take a look at McFadden's paper, that's really what he studies, but it's not the easiest paper actually to get through. You know, but when you set it up as a method of moments problem, you basically have a GMM estimator. So the variance formulas, you know, this is for the standard GMM estimator. Let's see, like DVD inverse, you know, the same formulas that we did before. The only difference is this term here. Okay, so this term adjusts for the fact that, you know, R is a number of Monte Carlo draws. So this adjusts for the fact that you're doing a simulation. So, and this is what's derived in McFadden's article, that he shows that this is, you know, a simple adjustment factor to adjust for the fact that it's simulated. Okay, so that's how you can derive out the variance of the simulated method of moments estimator. Okay, and then just a couple other remarks. I mean, there's actually a nice, I guess I don't have it in the slides, but there's a nice JEL article by Steve Stern that kind of reviews a lot of things about simulation. Because you can simulate with maximum likelihood. Like, you can always do the likelihood and simulate it. Okay, it's just in this, and a lot of times I use simulated maximum likelihood. So it's not that people don't use it. It's just in this context, you know, it works better to, well, an advantage in this context, you know, of estimating these probabilities from a random utility model is that the simulated method moments does not require that the number of draws goes to infinity. So it's consistent for R fixed. Okay, whereas usually simulated maximum likelihood does require that R goes to infinity for the asymptotics to go through. Okay, but you can do either one. So like when I use these methods, oftentimes I use both. So simulate maximum likelihood or simulate method moments. You know, and you can see, even though the model I did had one only had taste heterogeneity and the other one only had preference heterogeneity, but you can easily have a model that has both, right, that combines both. Okay.